Good evening all, and welcome to tonight's TI Technology webinar hosted by Texas Instruments Australia. We are really excited to bring you mathematical methods. And at the moment, I'm trying to get my screen to move on. There we go. And we're looking forward to hearing what these fantastic two presenters and teachers from all over Australia have to tell you about Mathematical Methods Unit 4. That is Mr. Frank Moyer and Stephen Crouch.
G'day.
My name is John Bayman. I am your host for this event. I teach mathematics to Year 7 to 12 students at Lachlan Catholic College in Darwin, where I use TI technology to help students make stronger connections in their understanding of mathematics. And I'm very excited to introduce our first panelist this evening, Mr. Frank Moyer. Good evening, Frank.
G'day.
Frank has vast experience in teaching mathematics, curriculum development, and sharing his knowledge at national and international conferences. Frank is also passionate about rich TAS and the use of CAS to strengthen and deepen students as well as teachers' understanding of various mathematical concepts. So Frank, thank you very much for joining us this evening.
Pleasure.
Our second panelist for this evening is Mr. Stephen Crouch. Evening, Stephen.
Good evening, John. Good evening, Frank.
So Stephen is a very talented and passionate mathematician who relishes the challenge of teaching specialist maths as well as methods to senior students and striving to support every student to understand various challenging concepts. His teaching is supported by his in-depth understanding of the course and his use of TI-Nspire technology. So Stephen, thank you very much for joining us.
Pleasure.
Now, that's enough of the intro. That's enough from me. I know that you've actually tuned in to hear from the experts, so I will pass you straight away over to Mr. Crouch. That's great. Stephen, we can see your screen.
Thank you, John.
It's all over to you.
Excellent. Thank you very much. Okay, so today I'm going to be, Frank and I are going to be looking at Maths Methods Unit 4. I'm going to be looking specifically at the integral calculus section of the course, and Frank is going to be looking at probability and sampling. So just as a quick list of what I'm going to be doing today, I've got a little demonstration on average value. I find that over my couple of years of teaching the average value, that there's a deep conceptual misunderstanding about what average value is. And today I'm going to show you a way that we can hopefully dispel any myths or any misunderstandings regarding that. After that, I'll be looking at integration from the point of a cumulative signed area. And then after that, I'll be moving on to areas for transformation. So these are typical Maths Methods Exam 2 technology active questions, where you're given a particular integral, and then you're asked to do something with the function that's being integrated, and then get the new area from there. So the first one is regarding average value. So unfortunately, a lot of students, when they first see average value, they simply see it as the evaluation of an integral. So they see, okay, f average equals 1 over b minus a, integral from a to b of f of x. Now, that's a very simplistic understanding behind it, and it really shows no in-depth conceptual understanding behind what the average value actually means. So what I like to explain the average value as, and some of you might also do this with your students, is that we explain it as the height of the rectangle that has the same area over the same width or same domain as that of f of x. So to show that concept of the average value, I've created a TNS file over here, and it starts off with the notes page, which is exactly what we'd pretty much write on the board. So you'd say we have a function f of x, the average value of that function over the interval a to b is f with little subscript average, and then you put the definition of it. And then what I've got is a dynamic maths box at the bottom where you can actually enter the whatever function you like. So a parabola is a really easy one to start off with, and this is what I've got here. So I've got the blue parabola over there, and I've got 2 points A and B at the bottom. What you can do is you can actually drag the points A and B as shown, and what you can see there is the red line, the red horizontal line there is saying what the average value is, FAV equals 3.6. And then at the top, I've actually got the integral of that function evaluated over the same domain. Now, unfortunately, we don't have the number of A and B at the bottom, so I've put it on the left-hand side here. So if you want to demonstrate a particular example, so you've introduced the concept and then you go to an example, then of course you can change f of x here to be whatever you like, and then come back over here, come back to this screen, and then slowly change your A to be, for example, 1, and then you can change your B to be for something like 2.5, and then you can show what that means in terms of the concept, and then where the 4.86 comes from, where that 4.86 comes from, and then I think that's a really good way to explain how the average value works out. What I also find a good way to explain average value, and I think this diagram does a good job of that as well, is that you can think of these two brown vertical dashed lines as the walls of a sandbox. So there's a big box of sand over here, and the profile of the cross-sectional profile of the sand starts over here at this blue section, starts at the left wall and goes to the right wall. So a good way to explain this is to say that the sand profile looks like that, and if you take a big hammer or some large cross-sectional area object and you flatten that sand profile down, what is the height that the new sand profile would be? And then you could say, okay, with this particular example, the height of that sand profile would now be 4.86 centimeters, meters, whatever your unit of choice would be. So of course, doing it that way is an excellent way to introduce average value. And then of course you can then bring in exam style questions such as the sand profile that I said, because I think in a few past exam questions, there have been instances where we have been given a function and then words such as the particular material has been bulldozed or something similar to be flat. What is the new height after this operation has been performed? And sometimes what a student would see that, they'd see that and they freak out because they don't see the word average value, they don't think of average value. So explaining it in a way like this and making it dynamic and interactive like I'm showing here would go a really, really long way to helping students see that. I've shown my students this particular interactivity, and they've walked out of the class just, their faces beaming because they finally understand what's quite a simple concept, but can be quite difficult to get your head around if they're not careful. So I just want to quickly finish off with this file. Yes?
Back on that other image of the live screen, which is fantastic, being able to move the values of A and B, just to confirm that where it says FAV in red, that's the actual area, just as the same as the integral area above. Is that correct?
That's exactly right, yes. Oh, so yeah, the area, and it also, that number should represent the height of the rectangle, isn't it?
Only if it's one wide, wouldn't it be?
Oh, that's right. Yeah, that's representing the area. Okay, I think I might have to fix it to represent the height. That's the area.
It's quite nice though as a visual. Like it's nice because when students see that integral in blue at the top and it's not changing, they think it's not changing, but it sort of is. It's changing always to the same number.
That's right. Yeah. That's right.
Whereas the graph below, you can see it much more easier what's going on.
That's right. I think, John, you've brought up a good point. I think I must have stopped up one of my calculations. So either the 5.79 down here or that one is wrong, because I want that one to represent the y value of that red line, because that is the average value. Because that's the height of that rectangle is the average value. Yeah. So I'll fix that up before we upload it. Yeah.
It's quite nice because there's many different ways you could do that. You could use the coordinate at the end of that higher horizontal line, or you could use the measurement between the dot A and up vertically upwards. So there's quite a nice couple of ways that you could get students to work that out. That's
right. Yeah. So apologies to everyone for any confusion over there. I'll have it fixed up before it gets uploaded to the TI website. Thanks for that. Okay. So what I'm going to do is I'm going to show you quickly how you can actually change this. So for example, let's say you want to put the cubic graph there. You just have to go change that to x cubed, and then you go back to 1.2, and suddenly you've got the cubic graph there. And as you can see, the areas, so the area here and the area denoted by the integral, and that they're in sync with each other. It's all very dynamic. So you can change this to whatever example you like. Even if you want, you can change it to, you know, a sinusoidal graph if you really wanted to, and then you end up getting similar things happening. So it's a really good way to demonstrate average value, of course, and you can change it to suit your particular circumstance. You can also, of course, transfer this file to students. They can play around with it and, of course, get a much deeper conceptual understanding of the concept, which is great. Okay, so moving on from average value, the next concept I wanted to look at is the concept of integration, but measured as a cumulative signed area. So what I'm going to demonstrate here is if you take the definite integral of a function and fix the lower bound or the lower terminal, and then keep the upper terminal a variable number, and then what happens is as you change that upper terminal, you vary that between a lower and an upper bound. What that integral does is it actually evaluates the cumulative signed area from that lower bound to the upper one. So going to that diagram, I've got a very simple cubic function here. It's got x-intercepts at -2, at 1, and at 3. So a very basic cubic function, as you can see there. And what I've got is I've got an area here. So I've fixed the lower bound here, as you can see, at -2, the first x-intercept. I fixed that there just because it's an easy way to look at it, because it's the first x-intercept and the area starts getting positive after that. So what I've got on page 1.3 is a spreadsheet, and what the spreadsheet has is a data capture. So what's happening in the spreadsheet is currently I've got the x value of that point there. I've got the x value as this big number. I think it's about -1.569 or so. And then on the right-hand side, on the second column, I've got the area that the shaded region represents. As you can see, it's saying area equals 1.19 as well. On page 1.2, I've got a graph here of x versus the cumulative signed area. So currently, as you can see, that's our x value, and that x value is -1.59 or so, as I said before, and the area is just above 1. So I'd like you to think about what happens if I start dragging this point, what sort of graph you would see appear on the screen. So I'm going to grab this point here and slowly move it to the right. As you can see, the area is increasing, which is what you would expect to see. And if I slowly increase that, go all the way to x equals 1, I've got an area of about 15.7. And this is a really good way to bring the students' attention to. So this is the area that we've accumulated from x equals -2 all the way to x equals 1. And then what happens is if I take that point and I drag it just a bit further, what you notice is that the area starts dropping again. And then the students might start asking, what's going on? Why is the area dropping? I thought this area is shaded. That area is shaded as well. Why is the area dropping? What's going on? And then, of course, that leads into further discussions regarding areas under the x-axis being negative, etc. So if we start dragging that more and more to the right, as you can see, the area drops even further. And I think there's some also conceptual misunderstandings that happen regarding turning points. A lot of students might think, well, what if this point goes to the right of the turning point? Will the area start increasing again? And of course, we as teachers know that the answer is no. The area still decreases because that's just getting more negative area. But some students might not think that, unfortunately. So again, doing something like this is a really good way to get them onto that. And then, of course, I can take it further after x equals 3, and slowly you see the area increasing again. So once this is done, once you've generated discussion regarding all this, you can come back to the scatter plot and you can actually see what's happened. The area has increased up until x equals 1. So at x equals 1, what's happened is we've accumulated more and more positive area. Then at x equals 1, it started dropping. And we saw that from a graph. Between x equals 1 and x equals 3, here's x equals 1, there is x equals 3. Between those two values, our graph actually dropped. And then after x equals 3, between x equals 3 and x equals 4, our area slowly started increasing again. So we've got a new graph now, and you can actually use this demonstration as an introduction to integration. The really good thing about this is you can use it at the very start of integration. So we've just finished your differentiation chapter in your course, and then you're introducing the concept of integration. You can definitely bring this up and show that over there. What's even better is even after you finish integration, you've gone through average value, you've gone through all the complicated concepts in integration. You can then come back to this and then talk about, okay, what is that as a function? So even as a quick checking point, you can draw a new graph here. You can change menu, graph entry, and function. And what you can do is you can actually put the integral, the indefinite integral of f of x. So f1 of x is our cubic. Integrate that with respect to x. And then what you see is you actually see this red graph over here. Now, of course, the reason why it's not aligning up is because we didn't look at any constants of integration. You see how I started my integration down at -2. We would have to look at an initial value and then get our value of plus c, etc., to get this to match up with that. But in saying that, if you take this integral and then you can start doing things like, you know, adding 5 to it or whatever, you can start adding numbers to this until it matches up with that. Because sometimes your students might not trust you, or they might not believe that the red graph and the blue graph are in fact the same thing. You can start modifying things, and there you go. I think we've got it there. 12, ooh, almost. This is a lot of fun. 12.5. Okay, I think that's pretty close. But yeah, so if students require any more clarification on this, you can quite clearly see that that red graph, which is the indefinite integral of our function, the blue function there, with an arbitrary constant added on, does in fact align up with the cumulative area that we found. So that's a really good way to introduce integration, of course, but also as an outro, so to speak, of the integration topic.
Stephen,
John, any yes?
Yeah, I think that's a lovely visual. I like the plus 12.5 because obviously when we normally start integration, we talk about having a constant, we explain why there's a constant there,
correct,
and then
yes,
we go into definite integrals, and if we're not careful, we don't explain why that plus c disappears.
correct.
But it obviously just cancels out. But this is a lovely way to show that it sort of doesn't disappear, it's still there.
Yeah.
And it's a really nice reminder for students, because obviously those are normally 1 or 2 marks in a paper that are unnecessary for students to lose. So I think it's fantastic. And obviously you could also do it by regression as well. You've got the data points now. You could actually match it with regression, couldn't you? Exactly
right. Yes, you can actually go to the spreadsheet over here, and then take this table here and apply some regressions to it. So yeah, it's really cool stuff. Yeah. Data.
I like that.
Yeah, that's right. It's really nice stuff. So hopefully that's been good. Of course, it goes without saying that all these files will be made available soon. So feel free to download these files when they're made available. Have a play with them. If you have any suggestions, of course, you can send them through. But most of all, just take them to your classrooms, project them up on the whiteboard, and have a go with this. And you can really get some really rich discussions with your students. And I think that's the amazing power of the Inspire technology. It can really inspire the students to look deeper into the concepts. Okay, so with the short little time I've got remaining, I'm going to head back to my main file here, and then go to the second last concept, or rather the last concept as a whole, which is areas after transformations. I'm sure you're all familiar with those questions in exam 2 that we get, where you're given a particular integral. So you're given a function. They don't tell you what the function is. They say f of x, g of x, h of x, etc. They give you a lower bound and an upper bound, and they specify that that integral is equal to some constant. Let's call it a for now to represent area. And sometimes you get questions where the multiple choice will ask you, if this particular integral is equal to a, then what is the integral after you've dilated the function by a factor of 2, for example? And typically what they do is they also add on a constant to the function. So you might get something like 2fx plus 3, and that's the new integral asked for. So sometimes students might struggle with that concept because they go straight away to their calculator and they're looking for a way to get that integral in there. Unfortunately, with f of x being unknown, it's a bit hard to get that going. So to help them wrap their head around this sort of idea, you can show a diagram such as this. So what I've got here is I've got the graph of sine of x plus 2. It's just a nice little periodic function of here, gone up by 2. And I've integrated, I found the integral of this. You can see with the green walls on the left and right. I've integrated that function between these two x values. You can actually change it as well. Let's go between pi on 2 and maybe 2 pi, just as a matter of example. As you can see, the approximate area under that sine curve between pi on 2 and 2 pi is about 8.425. The red graph is exactly twice that. So if you dilate the blue graph by a factor of 2 from the x-axis, you end up with y equals 2fx, and the area, which is given by the orange walls, as you can see there, is 16.85 approximately, which if you double the green area, you can see that that is what you get. If you look at approximations, of course, in the first order. And then likewise, if you go to the third one, which is the black sine graph there, that is 3 times the blue one. And as you can see, that is given by the yellow wall there. Let me just quickly change that. It's a bit too thin. There you go. I think that fixes it. So we can do that. And between these two walls, you can get the area of 25.274, which is about 3 times the 8 area that we got at the bottom. So that's not just for these two values. You can grab this bottom point and move it to any place you want, and the relationship continues to hold that the yellow area is 3 times the green, and the orange area is twice the green. So that's when you dilate by a factor of a certain number from the x-axis. Your area also enlarges by that same factor. Again, because this is very visual, hopefully when the students see something like this, it gets stuck in their mind, and when they get a question like that on their end-of-year exam, which is almost guaranteed, then they'll be well aware to tackle it without any difficulties. So now on to the final one, which is translation. So of course, dilation is not the only transformation that you can apply to a function. Another common one is a translation. So with the translation, it's very much the same setup. However, we're just translating upwards by a value of k, or even downwards, the same concept applies. So what happens is that area that we get will increase by the area of a rectangle, and the area of that rectangle is simply a rectangle whose length and width are b minus a, so that's the width of the domain of f of x, and the width of that rectangle would be k, basically the amount of the translation. So again, we've got a very similar setup. I've used the same graph here just to keep it consistent. So the blue graph is sine of x plus 2. The red graph is sine of x plus 2 moved up by 1, and the black graph is sine of x plus 2 moved up by 2. So what we've got is, again, a very similar setup where I've got two variable domain endpoints. And as you can see, the area, the green area, which is under f of x, is about 12.566. And the orange area, which is f of x plus 1, is basically the area that we've added on from a rectangle. So the area of a rectangle, for example, with this one, so if you go from pi on 2 to 2 pi, that is a width of 3 pi on 2. So if you take a rectangle with the width of 3 pi on 2 and with the width, sorry, a length of 3 pi on 2 and a width of 1, then the area of the rectangle is, of course, 3 pi on 2, and that is what adds on to 8.425 to get 13.137. So you can, of course, go to the scratchpad or to a calculator page, punch the numbers in, and then out comes the number, and hopefully that number will agree with the 13.137 there. So I'll quickly have a shot at that just to see that everything works out fine. So if you take 8.425 and add on 3 pi on 2, you can see you get 13.137, which does agree with the orange area there. So of course you can bring out more discussion about why that is, especially in regards to an integral. So when you integrate f of x plus 1, that also brings the students' minds back to the rules of integration, which is integration works individually over sums. So the integral of f of x plus 1 is the integral of f of x plus the integral of 1. Then when you integrate 1, you're actually just integrating a flat line, which does give you a rectangle. So it actually leads to some very rich discussions that you can have with your class, and hopefully you can get some ideas back from the students and get ideas from them too. And again, the really cool thing about this is you can change f1x to be what you want. So you can change that to be a cos if you'd like, and the same thing happens. And you can change it, and everything is dynamic, everything is linked. So you just have to change f of x, and then the graph will change. Of course, the red and the black graph are piggybacking off f of x, and then these 2 points over there don't really care about what f of x is, as long as it's not too below the x-axis and you can't see the function anymore. But that is the idea of what's going on. So hopefully that's given you a broad understanding of how powerful the TInspire technology is when being used for integral calculus. I'm going to stop it there and pass it back to John, who's then going to pass it over to Frank, where he can show you probability and sampling. Thank you.
And Stephen, while it's still on you, I was thinking that you could easily use coordinate geometry and draw the rectangle below, and you could even use variables, couldn't you, with some of those values, either the width or the height, and actually show the values changing and how, you could use a scratch. That's really nice, but you actually could do it that way as well.
That's right, exactly. Yeah, you can use the geometry menu is really powerful. You can start drawing rectangles from there to there and make it a variable height as you please. But yeah, it's really
going back to the other one. I think students get that one more, but on the other one that you were showing, I think that really freaks them out. That hang on a minute, you double it, the shape completely changes. So how can the area just be doubled? Like, it just doesn't. Even when you see it there, it doesn't make sense. And I think that's what you said is the power of the Inspire technology, and actually having those visuals and especially if they create them, is so important and so enriching for them as learners.
That's exactly right. Yeah, I just wish that that back when I was in school, that we had this power available to us to visualize it. But well, the students of today have that, which is good. So if we make it, if we take advantage of it, then the conceptual understanding will increase. Exactly right.
Yeah, exactly right. I think it's so important. I saw a nice cartoon recently of talking about students and how they can see so much interactive stuff now, and then therefore in their classroom we've got to sort of not match it necessarily, but we've got to actually try and use some of that and embrace it and use it in the classroom. So this is a fantastic approach. So thanks, Stephen. Right. That was wonderful. And Frank, I can see your screen. It's all over to you.
Oh, excellent. Okay, thank you. Good evening and welcome, everyone. I'll be talking about probability and statistics area of study. And first of all, I wanted to have a look at the probability mass function of the binomial distribution and explore it using dynamic features of TI-Nspire. Now, in the VCE study design, it does specifically talk about the effect of variation in the values of defining parameters on the graph of a given probability mass function. And that's what I'm going to explore. Now, the probability mass function when the study design first came out, teachers were a bit confused about that. The probability mass function is just a function that defines the distribution of a discrete random variable. So for a continuous random variable, it's a probability density function. For a discrete one, it's a mass function. Okay, so the example I'm going to have a look at is I'm going to set up table and graph for a random variable x, which is binomially distributed with n and p as the defining parameters, and I'm going to have sliders that can change the values of n and p. I'll explore the expectation of x and also explore a model that I can use to see if I can find another function that can model that distribution. Okay, so to save time, I've already put in a data and statistics page, I've put a slider with n and p. By the way, to put sliders, it's just menu and actions and insert slider in data and statistics. And so n and p are defined by the slider. Now I'm going to operate this from a spreadsheet. Now in this column I've got x. X is going to be the number of successes, and I'm going to use a sequence command where the expression I'm just going to call k. The variable is k, so it's just going to return the values of k, and the values are going to be from 0 to n. And the reason I've done it this way is because as I change n on the slider, then the spreadsheet will update automatically. And here I'm going to have the probability. Now it's a binomial probability, so I'll go to equals and I'll go to the catalog, and it's B for binomial. So I want the binomial PDF, and down the bottom you can see the syntax, although actually I think we're going to get a dialog box anyway, so it's NP and the value. So the number of trials is determined by the slider, N. I'll tab down. The success fraction, the probability of success in a single trial, P, it's determined by the slider. And X is going to be whatever's in column X, or in fact everything that's in column X. And once again, I'm going to have to resolve whether I'm talking about a variable reference or a column reference. In each case, it's that's a bit cumbersome. We're there. And I'm going to do one more thing. I'm going to have the product of X times its probability. So I'm going to have X multiplied by its probability. And I think I've got everything I need. So I'll go back to the data and statistics, and here I'm going to select X, and I'm going to graph that against its probability, Px. And I can see a graph of the distribution. So if I change the value of n, then that will change, or I can change the value of P. But there's a few other things I can do. I can also go to Menu, and under Analyze, I can put in a plot value. And the plot value that I'm going to put in is the sum of X times its product. Sorry, the product of X and its probability, which is the definition of the mean or expected value. Oh, and that's interesting because so the expected value worked out on a first principles basis when I have n equal to 12 and p equal to 0.4, 4.8, which is 12 times 0.4. And lo and behold, it's always, and students can very quickly convince themselves that it's always n times p, which is rather nice. Now, I'll just increase this to 20. Okay, and I'll just zoom to the data. So control menu will get you the context menu. Whoops, I didn't want to do that. I wanted to just zoom data. Okay, now that looks fairly symmetrical. So I wonder whether how well a normal curve would fit that binomial distribution. So let's investigate that. So if we go to Menu, under Analyze, as well as being able to plot a value, you can also plot a function. So let's try the normal PDF. So if I go to Catalog, and normal starts with N, so I'll hit the letter O and go back up. Normal PDF, and the X value is just X. I'll tab down. Now, I've already convinced students it's N times P as the mean. And now this, we would probably, for today's, I'm just going to just accept that it's the square root of N times P times 1 minus P. And bingo. So that seems to fit pretty well, at least when P is 0.5. But actually, it's pretty good anyway. Now, I think that this is a really good illustration of why, when we get to the statistical inference, that we can model the sampling distribution with an approximate normality. So the approximate normality of the sampling distribution is fairly obvious if students have done this beforehand. And that's what I'm going to move on to now. So I'm going to move on from there to sampling. So statistical inference for sample proportions, looking at the distribution of sample proportions and confidence intervals. So we'll start with the real examples. In July, the Australian newspaper published a news poll where 1,609 voters were asked their preferred party if a federal election were held that day. And the news poll results were something like this. On a two-party preferred basis, 788 voters favoured the coalition out of the 1,609. Okay, so the sample proportion, which we call P hat of coalition voters on a two-party preferred basis, is that fraction there, which is a P hat value of about 0.45. But how trustworthy is that statistic? After all, only about 1,600 voters were sampled. What about the other 16 million voters on the electoral roll? They weren't asked, so how can we know whether this is trustworthy? Well, to see the trustworthiness of sampling, we need to understand how sampling behaves. And that's where simulation using TI-Nspire really helps students understand how sampling behaves, and they can come up, they can come to understand the idea of the sampling distribution. Okay, so we're going to have a look at repeated random sampling, because in statistical inference, we see how reliable something is by seeing what happens if we repeat it many times. Okay, so in this simulation, we're going to assume that at a particular time, the sample proportion, the population proportion of coalition supporters is 0.5, and we're going to take surveys of sample size 20. So we're going to take lots and lots of surveys with N equals 20 each time, and P is 0.5. Now, of course, normally we wouldn't know the value of P. If we knew the value of P, we wouldn't have to run the survey or the poll. We're assuming it in this case to help us understand how it behaves. Okay, just notation, the capital X is the random variable, in this case for the number of coalition supporters. Capital P hat is the random variable that denotes the proportion of coalition supporters. And so from that, we've got these formulas which arise naturally from that definition. So each value of lowercase p hat is a point estimate of the true population proportion. So the random variable capital P hat is called the estimator, and lowercase p hat is the estimate, the actual value. Okay, so x is binomially distributed with n equal to 20 and p equals 0.5. Why is it binomially distributed? Because either the person surveyed is a coalition supporter or they're not. And what we're going to do is use random binomial function in order to conduct the simulation. Now, I've already made a partial start on this. So here, at the top here, I've got a data and statistics page with a slider D. D is where I draw another sample or conduct another survey of 20 voters. And down here, I've got a notes page where I'm going to input my random binomial function. And I'm going to capture those values into a spreadsheet. Now, many textbooks will do something like this in order to do the simulation. They'll start off with random binomial. So I go to Catalog and R, random binomial, it's MP and number of trials. So N was 20, P was 0.5, and so that's, if I just did that, that would give me the result of one survey, one trial of 20 people. Now, a lot of the textbooks say, oh, you know, you could sort of see what happens if you do 200. And I get a list. And perhaps I could store that as a variable capital X. In this case, I'm going to use lowercase x because it doesn't like, and there you go. That's your sampling distribution. The trouble is, if you do that in the first instance, I've found that students find that rather confusing. They can't get their head around the fact that that isn't, that you haven't surveyed 200 people. You've actually conducted 200 separate surveys. So I think it's better if they see that happen one at a time, one survey at a time in the first instance. Now, something else you can do here, by the way, is if you have plus D, where D is controlled by a slider, minus D, then every time you change the value on the slider, it will re-evaluate. So that's just a neat trick. Now, that's not the way that I would start doing this simulation. The way that I would start is with just a single variable, just a single survey. So here, in this case, there were just 13 successes out of 20. So that's one survey. Then, what I'm going to do in this column, which I've called X underscore, I'm going to capture the value of that X. So to capture, you can go either to menu and data, or even quicker, control menu, get the context menu, data, data capture, automatic data capture. So the variable I want to capture is X. The 1 is just code, meaning that it's automatic. Now, if I were to do that, I would get results that weren't perfectly accurate, because if you were to get the same result twice in a row, the spreadsheet would only capture it once, because it would say, I've already captured that value, I don't need to capture it again. So you need to let it know that to look for anything that has changed. So if you put comma D, now this is something that I haven't seen, I picked this up at a conference overseas, and I haven't seen it in any manual, I haven't seen it anywhere else, so I think it's little known, but that is a way of getting accurate results when, even if you get two results the same in a row. Okay, and here the proportion is just whatever is in column x underscore divided by 20. Okay, so now I can go to here, and I don't want the x value, I actually want the proportion. And I'd better change the scale, so Windows settings, from 0, tab to 1. Okay, so this time I've got 13 successes. So that's in one survey of 20 people. Now the other thing you can do is, and this is the other reason why you don't want in one fell swoop to see the result of 200 surveys. If you do it one by one, students can see something else that's really important. If you go plot value and you want the mean of that column P hat, okay, there's only one value there, so that's the mean. Okay, I'll press D. I've now got another value, and now I've got the mean of those two. So another survey. So each time I'm carrying out a survey of 20 people and seeing how many successes, where the definition of success is finding a coalition supporter. Okay, and we can see that the mean dances around. But the important thing is for students to notice that as the number of surveys increases, that it converges towards 0.5, towards the true population proportion. Okay, and that is really powerful because it shows that, hey, actually, sampling behaves this way. It actually is valid to that if you were to do the survey many, many times, you would expect, or the mean value would actually be the true population proportion. The other thing you can do here is see how close to the normality it is. So what this is doing, what I did there was control menu, the context menu, and select the normal probability plot. So this is the actual value against the expected value if it was perfectly normally distributed. So if it was perfectly normally distributed, all points would have to be on that line. Now we see that they're not exactly on that line, but they're actually not that far off. Okay.
Well, Frank, that's amazing how quickly we can go through that sort of data. And like you said, that visual, like Stephen said earlier, is so powerful because you can quickly go from a couple and shoot up like you did, and the visual there, and then allowing it to see what the prediction is fantastic. Yeah,
that's right. And so this technology, I mean, when this topic was first taught, or was last taught in Victoria back in the 90s, it wasn't a huge success. Students learned how to answer exam questions, but didn't really understand what was going on. And I, as a teacher, I'm not sure that I fully understood what was going on. This technology allows you to actually understand, to actually see interactively what's happening. Okay, so what we just saw was a model of the sampling distribution of P hat. So sampling distribution contains all possible samples of the same size drawn from the same population. Okay, so I'm going to skip all that, and we can do some algebra, and we can show algebraically that the expected value of P hat really is P, which is what we saw by finding the mean of the values. And that's where I think it's really important in the first instance for students to build up that model of the sampling distribution one survey at a time, so they can see that it really does converge to P. And we can also do some algebra to show that the standard deviation of p hat is the square root of p1 minus p over n. Of course, in practice, we normally don't know what p is, otherwise we wouldn't need to do the sampling. So what we do is we approximate p with our p hat. So instead of the standard deviation, we call that the standard error, which is just an approximation of the standard deviation. Okay, so, whoops. Okay, so in the next bit, what's the effect of changing the sample size? Now, this is now that students understand the sampling distribution, we can sort of show them 100 or 200 at a time. And if we go from a size of 10, 20, 30, 40, so we see that the standard deviation gets less, so the distribution is not as wide, which is what we would expect because we saw that the standard deviation has n down the bottom. As n approaches infinity, the standard deviation will approach 0. Okay, and so we see that the spread decreases as the sample size increases, and the symmetry also increases with sample size. And next, now let's go back to beginning. Okay, the effect of the population proportion on the distribution of sample proportions. So this time I'm going to vary. So with a sample size of 20, I'm going from 0.05 as the population proportion, not very symmetrical, although if we increase the sample size, it actually does become more symmetrical, even for fairly extreme p-values. Okay, we see that it's widest when p is 0.5, has the biggest spread, but it's also the most symmetrical at 0.5. And so at extreme values, less symmetrical, but less and less spread. Okay, I'm going to skip all that. So for a given sample size, the spread and symmetry of the sampling distribution depends on the population proportion, with the spread being greatest at 0.5 and becoming more symmetric as you get closer to 0.5. Okay, so now we're going to have a probability model. We saw that the distribution can be modeled by the normal distribution when conditions are favorable. So the approximate normality, when is it valid to model with the normal distribution? Well, many statisticians say when the sample size is big enough that you have at least 10 successes and at least 10 failures. Other statisticians say, no, that should actually be at least 15 successes and at least 16 failures. There's no clear-cut answer. Okay, and just in the last few minutes that I've got left, confidence intervals. So why do we need to go further than just reporting the value of p hat? So what do we mean by a confidence interval? Well, the problem with only reporting p hat is that it's really not enough, because we also need to give some information about the precision of that estimate. And that's what the confidence interval is doing. It's giving not just the value, but also an interval that is likely to contain that value. So the formula that students see on the formula sheet and in textbooks is the p hat plus or minus z. Z is the quantile from the standard normal distribution, bearing in mind we're modelling this as a normally distributed random variable, and we use p hat rather than p because we don't know what the p value is to put in the standard deviation. So that's an approximation to the standard deviation. That z times that standard error is called the margin of error. Okay. The level of confidence, so the value of z, and now people who have seen my webinars before have seen this before. So 0.99, 99% confidence interval, 2.58 is the quantile, 95% confidence interval, 1.96, 90% confidence interval, 1.64. Okay, and now this I set up. I had a more primitive version for simulating confidence intervals, and it was my colleague Ray Rosen said, well, you know, couldn't we actually make it turn red or something when you have a confidence interval that doesn't contain the population proportion? So I actually spent a bit of time and I actually got that happening. So what this is showing, the true population proportion is 0.65. That's the point estimate in red, and that's the confidence interval. So the half interval from the red dot to the boundary is the margin of error. So that one contains the population proportion, the true population proportion, and that one. Okay, well, that one doesn't. So we've got two that don't. 3, 4.
This is a great visual, Frank, as well. You've done a great job here.
5. Okay, so I think that after Ray prompted me, I think this is probably better. Actually, that's perfect, because 5 out of 50, for a 90% confidence interval, 5 out of 50 did not contain, in other words, 10% did not contain the true population proportion, and 90% did. And that is exactly the meaning of a 90% confidence interval. Okay, so it does not refer to, so in the long run, an approximate 90% confidence interval means that the true population proportion will be contained 90% of the time, and it won't be 10% of the time. And there's just one more that I want to do. Okay, so this shows 99, 95, 75, and 50, and we see the idea is that if you want more confidence, you have to, the trade-off is that you need a longer interval, so more margin of error. So more confidence means a greater margin of error, so there is a trade-off. And my time's up, so I'll leave it there, and thank you very much for listening.
Wow, thank you very much, Frank. I think both you and Stephen really gave us some fantastic things to take on board and really make some of those harder concepts for students to really understand what's going on, visual, and smash through a lot of data. That was fantastic. I think you're right, especially with probability, that students can answer questions, they learn to answer questions, but they actually don't really understand what they're doing. And that there's some great activities there that I know you share on the on-demand page that teachers can use in the classroom. So thank you. Are you still there, Frank?
Oh, yeah, sorry. Yes.
Good. That's okay. So we're going to begin wrapping things up. If you do have any last-minute questions, please try and get those answered. I know Stephen and Frank will be watching the chat windows and the Q&A window, and so they will endeavour to answer them for you, or they will add them to planning of future webinars. When we leave the webinar tonight, a brief survey will automatically appear here in your browser, and your feedback guides us as we plan future online events. We will listen to your feedback, so we do hope that you share your thoughts in a post-webinar survey. And your all-important certificate of attendance will be emailed to you in the next 48 hours, along with a link to the on-demand and YouTube versions of the recording, as I mentioned earlier, as well as the relevant documents to both Stephen, I know that he's fixed up that one about the height, and Frank, you this evening.
Yeah.
Thanks, Stephen. After we leave tonight, if you do need some post-webinar follow-up, please feel free to phone or email TI. I know they'd love to hear from you and either answer your questions for you or put you in touch with experts like Frank and Stephen. And that brings us to the end of tonight's webinar. Thank you so much, Stephen and Frank, for everything you've shared with us tonight. I've really appreciated it, and I know the participants have too from the feedback we've had from them. So thank you very much.
Thank you.
Cheers.
And thank you, everyone, for joining us. Whether you're watching it live or on demand, we really appreciate you spending the time watching it. I hope you found it useful, and we hope to see you back online again soon. Thank you, and good night.
Thank you.
Good night.
Good night.